Hey everyone, and welcome to another explainer from CodeAccessHub. Today, we're going to talk about something that's, well, the very bedrock of blockchain, digital signatures. Think of them as the cryptographic handshake that makes this whole decentralized world possible. All right, so here's what we've got on tap. We'll kick things off with what these digital handshakes are all about. Then we'll pop the hood and see how they work. After that, we'll take a tour of the different algorithms out there, see why they're so indispensable for blockchain, and wrap up by looking at the risks and what's coming next. Okay, so let's jump right in. What is a digital signature, really? I mean, how is it any different from the one you scribble with a pen? Well, let me tell you, it's a whole lot more than just a digital version of your handwriting. You can think of it like a high-tech cryptographic seal of approval. It's a way to prove that a digital message is legit and that nobody's messed with it. And the magic behind it? It's all built on something called public key cryptography, which, as we'll see, uses a special pair of keys to lock things down. And this is where things get really cool. Your handwritten signature, it looks the same on every single document you sign, right? That's a one-to-many kind of deal. But a digital signature is the complete opposite. It's totally unique for every single message it signs. It's a one-to-one relationship, and it's mathematically tied to that specific piece of data. No two are ever alike. So, when you boil it all down, it comes to these three things: authentication, integrity, and non-repudiation. These are the pillars that build all the trust we need to interact securely online. And in a world like blockchain where there's no central authority, well, that trust isn't just important, it is absolutely everything. All right, so how does this magic trick actually work? Well, it all goes back to that pair of keys we just mentioned. You get two keys that are mathematically linked together. One is your public key. You can shout that from the rooftops, share it with anyone. But the other one, that's your private key, and you have to guard that thing with your life. So here's the process. First, you take your message, let's say it's a crypto transaction, and you run it through a special function that spits out a unique fixed-length digital fingerprint. We call that a hash. Then you take your super secret private key and use it to encrypt, or basically lock up, that hash. And voila, that encrypted hash is your digital signature. Okay, so how does someone check it? It's actually pretty clever. The person who receives your message uses your public key to unlock the signature and reveal the original hash. At the exact same time, they take the message you sent and create their own hash from it. Then they just compare the two. If those hashes are a perfect match, boom, you have mathematical proof that the message is authentic and hasn't been touched. Now, you might be thinking there's just one way to do this, but nope. There's a whole menu of different algorithms out there. Each one has its own strengths and weaknesses, which is why you see different blockchains choosing different ones. It's all a trade-off between security, privacy, and how well it can scale. Let's start with a big one, ECDSA. This has been the go-to algorithm for both Bitcoin and Ethereum for years. It's all based on some pretty wild math involving something called elliptic curves. The big win here is that it gives you top-notch security with keys that are much shorter and more efficient than older systems. But it's not perfect, especially when you need to handle a ton of transactions. Next up, Schnorr signatures. Now, these were a huge upgrade for Bitcoin, brought in with the Taproot update. The killer feature here is something called linearity. Fancy word, but all it means is you can basically add signatures together. So you can combine a whole bunch of signatures into just one, which makes those complex multi-signature transactions way lighter, cheaper, and a lot more private. And then you've got BLS signatures. This is a real game changer, especially for proof-of-stake systems like the new version of Ethereum. I mean, think about it. You've got thousands of validators who all need to sign off on blocks every few seconds. You can't process all those signatures one by one. BLS is the solution. It lets you bundle all of those signatures into a single, compact one. It's an absolute necessity for that kind of massive scale. So here's a quick cheat sheet for you. You've got ECDSA, the efficient, tried-and-true standard. You have Schnorr, which is all about smart aggregation for better privacy and scale. BLS takes that aggregation to a whole new level for massive networks. And then you have something totally different like ring signatures, which is what privacy coins use to hide the sender's identity by mixing their signature in a crowd. Pretty cool stuff. Okay, so we've covered the how, but let's talk about the where. In blockchain, digital signatures aren't just some nice-to-have feature. No way. They are the absolute core engine that authorizes every single action that happens on-chain. I mean, think about it. Every time you spend crypto, vote in a DAO, or trigger a smart contract, what's happening under the hood? It's a digital signature, proving you're the owner and giving the green light. Take them away, and the whole system of decentralized trust just falls apart. They are, without a doubt, a fundamental building block of this entire space.
And this is a fascinating evolution. For the longest time, only regular user accounts, the ones you and I control, could actually sign things. But with new standards like EIP 1271 on Ethereum, smart contracts can now verify signatures themselves. This is huge. It opens the door to all sorts of powerful new tools, like smarter multi-sig wallets and way more complex steps.
But of course, it's not all smooth sailing. The technology has its challenges. At the end of the day, the security of a digital signature is only as strong as the code it's running on, and, more importantly, how well you protect that private key. So let's take a look at the risks we're dealing with now and the massive threat that's looming on the horizon. What this really shows is that the weakest link usually isn't the complex math behind the signatures. It's us. It's human error and buggy code. You've heard the saying, not your keys, not your crypto, and it is 100% true. Keeping that private key safe is literally everything. And that brings us to the elephant in the room, the biggest future threat of all, quantum computing. See, all the cryptography we use today relies on math problems that are just too hard for our current computers to solve. But a powerful enough quantum computer could potentially crack them, just like that. And if that happens, all of our current digital signatures could become worthless overnight. So yeah, that pretty much sums up the challenge we're facing. The good news is that cryptographers are already on it, working hard on new algorithms that are resistant to quantum attacks. But make no mistake, it is an absolute race against time to get our systems upgraded and protect the foundation of our entire digital world before that quantum threat is real. So if you enjoyed diving deep into core concepts like this and you want to keep exploring the building blocks of blockchain and Web3, definitely check out the CodeAccessHub channel on YouTube. We've got plenty more explainers just like this one. Thanks so much for tuning in.